In my previous video, I introduced vectors and I discussed something called a unit vector. And all a unit vector is a vector that has a magnitude or a length of 1, and that's how it's notated here. Um, if we want to take any vector and we want to convert it into a unit vector, all we need to do is divide that vector by its magnitude. And this makes complete sense if you think about it. If you have a vector that has a magnitude of, let's say, something like 7, then if you take that vector and divide it by its magnitude of 7, then you're left with a vector that has a magnitude of 1. So let's do an example of this just to start off. So suppose we had a vector v, and vector v had written in component form is at 7, -3. And what we want to first do is we want to find a unit vector, and then we'll check to make sure that this new unit vector does indeed have a magnitude of 1. So we're going to take the vector v here, and we're going to start by finding its magnitude. So we're going to say, all right, the vector's magnitude is simply the distance formula. So we're going to take 7 squared plus -3 squared. And that's going to give me the following. We're going to say vector v's magnitude is simply 49 plus 9. That's root 58. And we don't have to simplify this right now. In fact, that would just be 2 times 29. So that's about as simplified as it gets. So here's our vector's magnitude. Now we're going to take our vector v and we're going to divide it by its magnitude. Again, this is so that we can get a unit vector, one with a magnitude of 1. So we're going to take vector v and we're going to divide it by its own magnitude, which is going to be vector 7, -3, and we're dividing that by its magnitude of root 58. Let me make this a little bit smaller so we have some room to work with. So that is going to then just be the following. Let me actually write it down here. That's going to be, well, if I take 7 and divide it by root 58, so 7 divided by root 58, and then -3 and divide that by root 58. So here is our unit vector, and I'm just going to call this unit vector something like u, just to indicate that it's our unit vector. So this is a different vector. This is a vector that is going in the same direction as vector 7, -3, as vector v, but this vector simply has a magnitude of 1. And we should be writing all of our vectors in simplified form. In other words, we should be rationalizing these. So this is 7 root 58 over 58. Like that. And then this would be -3 root 58 over 58. Now, to be clear, I'm not going to erase this because I'm actually going to use this. It's actually easier to work with our non-rationalized form when we do our verification. So let me verify this here. So I'm going to say verify. So we found our unit vector as it's written down here below, and I just want to check to make sure that this vector does indeed have a magnitude of 1. Well, how do I do that? I'm just going to find the magnitude of my unit vector here. So the magnitude of this. And so if I do the distance formula, you can see now why it's easier to work with our non-rationalized form, because I can just say 7 over root 58, all of this squared, plus -3 over root 58, all of this squared. And having it non-rationalized allows me just to write this as 49 over root 58 squared is 58, plus -3 squared, that's 9 over 58. And I get root 58 over 58, and that's just going to give us 1. So what I've just done there is I've verified that this unit vector I found does indeed have a magnitude of 1. This is not something that we'd have to do all the time, but just something that we at least now know how to do. So I would encourage you to pause the video and now try this next problem. Try this one on your own. See if you can find a unit vector that's going in the same direction as 4, 1. Well, if you've given this problem a go, I just want to make sure that conceptually you're understanding what we're doing here. We currently have a vector u that has a terminal point of 4, 1. So this is what vector u looks like. There's vector u. This is at the point 4, 1. What we're trying to do is trying to find a vector that is also going in the same direction, but is going to have only a magnitude of 1. So to indicate this, again, vector u right now, hopefully what you did was you found the magnitude of vector u, which is just 4 squared plus 1 squared, which is root 17. And then we're going to call our unit vector let's just say our unit vector is, I don't know, v. Our unit vector v is going to be this current vector, 4, 1, divided by this magnitude. And so what that gives me then is 4 root 17 over 17 over root 17 over 17. And so this vector, this unit vector that we just found, is a vector that is going in the same direction, but has a much shorter magnitude. So vector v would look something like this. And again, this is a magnitude of 1, right? But it's a vector that's going in that same direction. Now, all of these unit vectors here, again, a unit vector is simply a vector with a magnitude of 1. There are things called standard unit vectors, which are vectors that are often described with the variables I and j, and it's simply just describe a specific type of unit vector. Vector I is a unit vector that is going straight up on the y-axis. So vector I is, on the x-axis. Vector I goes along on the x-axis. So it has a magnitude of 1. So it has a terminal point of 1, 0. Vector j is a unit vector that goes up vertically on the y-axis. Now, oftentimes, given this information, we will express vectors using these standard unit vectors. And when we do that, it's called a linear combination, or often called a standard form. So commit that to memory, knowing that we call this a linear combination, or when you're asked for standard form. And we call it standard form because we're using standard unit vectors. So for example, if you're given a vector v that has the terminal point -2, -3, or component form is -2, -3, all you're doing is rewriting this as something like v in standard form is -2i minus 3j. And all this really means is that you have two I vectors, or excuse me, -2i vectors. You're going to the left to kind of draw this out. You're going to the left 2 i's, and then you're going down 3j's. So this would be -3j. And this is where you end up. That's what that vector, same vector that's currently in its component form, that's what it looks like in its standard form, or as a linear combination. All it is another way of expressing the same vector, just in using its standard unit vectors. So go ahead and pause the video and try these problems here where you're just expressing these vectors as linear combinations and doing operations with them as in standard form. Next, I want to discuss something called direction angles. And so far with vectors, we've discussed how to find the magnitude of vectors, but the other part of vectors is knowing the vector's direction. And we express a vector's direction oftentimes by describing what we call its direction angle, or its angle of the vector as it opens from the positive x-axis. And we're accustomed to working with it because this is how we've discussed angles in trigonometry, starting with a positive x-axis. And now that we know what vectors are, we can treat them as terminal sides of angles on a unit circle. So again, if I can you see a diagram here, but it might help if I just kind of draw it from scratch as well. If you're given some vector v, let's say for example, if we're given some vector v here, and with this vector v, we see a vector v looking like this, what we can say here is, all right, this point here would represent our v sub x and our v sub y. And if that is our vector v, the question that I would pose is, how could I find this angle here? What would theta be? What can we use? Well, again, if we think back but not too far, we can just say, all right, I could drop a vertical down and treat this as a right triangle. And if we know that this represents our v sub x, this side of the triangle is our x value, or x component, our horizontal component, and our vertical component here is v sub y, just kind of pause the video and ask yourself, how would I be able to find theta here? What can I use? And the answer, hopefully, that you came to is trigonometry, specifically the tangent function. We can say that the tangent of our angle theta is equal to our opposite over our adjacent, or our vertical over our horizontal, or as we would write here, v sub y over v sub x. So we can just say to find a direction angle, to find theta, we can just simply do the arc tangent or the inverse tangent of our y over our x, or v sub y over v sub x. Just really make sure I emphasize that was a v, right? So if I wanted to find the direction angle of this example here, let's try this. The direction angle of vector v. Notice that this vector currently is in standard form. This is the same thing as vector v being -7, -4. Well, maybe just draw this out just so you can see what this looks like. We're going to have to say that this is -7, this is -4, and our vector looks something like this. What we're trying to find is this angle here. What is this angle theta? Well, we would find the arc tangent. Let me actually do this from scratch. We'd say theta is equal to the arc tangent of -4 over -7, or the same thing as positive 4 over 7. And when we find theta here, theta would then give us, let me do an approximate symbol, approximately 29.745. Now, wait a second and think about this. Why is our calculator giving us an acute angle when clearly the angle here that's shown is more than 180 degrees? Well, think back to the range restriction for inverse tangent. Our calculator is only going to give us a value between -90 to 90 degrees, not inclusive. And what it's finding is the angle, when I apply the tangent to it, is going to give us positive 4 over 7. That's the way we enter it into our calculator. So what is this 29.74 represent? This gives us our reference angle. So that 29.74, what they're giving us is this, because in the calculator's mind, what it's finding is actually this angle here. Or actually, I should say the calculator is actually thinking that we're doing this angle here to find the tangent of this angle, giving us an output of 4 over 7. 4 over 7. That's what the calculator thinks we're doing because of what it understands about the range of inverse tangent. So we're going to leverage that and we're going to say, okay, since we're treating that as a reference angle, that's fine. We know that that is going to represent this same angle over here. So this angle that we just found, that's what the calculator gave us. We're going to say that that is our reference angle there. So with that said, how can we actually use all this information? We'll say, all right, well, theta then has to simply be 180 plus this angle, which is theta is approximately 209.745. Okay? All right, let's try a few more examples. Let's find the component form of a vector. And this vector, what information we're given is we're told that it has a magnitude of 4 root 3 and its direction angle is 120 degrees. So let me just draw this. So what they're telling us is that this angle is 120 degrees, so it's 30 degrees past 90. Okay, so there's theta is equal to 120 degrees. There's our vector. That's the direction it's going, and it has a magnitude of 4 root 3. Its length is 4 root 3. What we're tasked with finding is what are its terminal points? Because if we know its terminal point, then we know we can write it in its component form. Well, how would we go about doing this? We would say vector v is equal to its magnitude times the trig functions of specifically cosine and sine of that angle. Because we know that the magnitude v multiplied by cosine of theta, sine of theta. Pause and think about why this is the case. we know that cosine of theta is equivalent to finding our horizontal component. This is our x. The sine of our theta gives us our y component, but treating them within the unit circle. So we multiply by the magnitude to get the actual x value. So in the context of this problem, we would say our magnitude, which is 4 root 3, times the cosine of 120 degrees times the sine of 120 degrees. Well, 4 root 3, these are angles that we can evaluate the cosine and sine for. This would be cosine of 120 is negative 1/2. The sine of 120 is root 3 over 2. And that would give us the following. We would say, after simplifying, negative 2 root 3 and 2 root 3 times root 3, that would just give us 6. So here's our vector v. So our vector v here has an angle of 120 degrees, a direction angle of 120 degrees, and it has a magnitude of 4 root 3. All right, let's do one more problem together. This time, let's find a vector given the magnitude of 7. So pretty similar, they're giving us the magnitude, but this time they're not giving us a direction angle, they're actually saying we want it to be in the same direction as this other vector, 2, 3. Now, there are a couple of options here, and one option is for us to find the direction angle using arctangent, and we could certainly do that. The one downside to this is oftentimes when we find a direction angles, we are finding an approximate angle. It's not always that we will get an exact angle. We'll be using an approximation. So how could we do this problem then so that we're not using an approximation for our direction angle? Well, the first thing we'd want to do is recognize that we've got a vector that ends up at 2, 3. So instead, our approach could be, let's find a unit vector that is going in this same direction. So find the unit vector first, and then simply multiply that unit vector by a scalar of 7. So find the unit vector first. Okay, so we're just finding a smaller vector that has a magnitude of 1 that's going in the same direction as this other vector, and then we'll just multiply by 7. So let's call this unit vector v. Let's just say, let's call this unit vector v. So our unit vector v, actually to start, we would need to know the magnitude of u. So let's start by finding the magnitude of u. So the magnitude of u is simply 2 squared plus 3 squared. That's going to give me root 13. So I'm going to take this unit vector v now. So this unit vector v is going to be 2, 3 divided by root 13, which is 2 root 13 over 13, 3 root 13 over 13. Okay, so here is our unit vector. This is our unit vector. So now that we have our unit vector, we're going to find our unit vector and we're going to multiply it by 7. And now that I read the directions a little bit more carefully, it asks for the vector to be called v. So I'm going to call this here just our unit vector. So we're going to now say vector v, let me try to switch this to a different color just to indicate that we're finding a different vector. Vector v is going to be 7 times our unit vector. Because our unit vector has a magnitude of 1, so we're going to multiply by 7. So we're going to say 7 times 2 root 13 over 13, 3 root 13 over 13, and this vector v is simply going to be 14 root 13 over 13, and 21 root 13 over 13, okay? So hopefully you're a little bit more comfortable now with working with finding direction angles and using direction angles or unit vectors to find other angles going in the same direction or some variation of such.